All right, so it might be a good time just to start talking about the utility measures. We probably won't be able to finish all of them, but I want you to get us talking and started doing things, especially to play with those measures and then how to implement them. And that's what some of you were asking through email earlier. And the methods for utility evaluation, so the slides, yeah, so the slides I put it up earlier today. And what we can talk about now is, yeah, so based on the Wu et al. Paper in 2009, they're mostly talking about global utility measures. So those ones, I mean, there are pros and cons of each method that they propose, and we can discuss them at the end once we go through each of them one by one. And I think it's useful. I mean, first of all, to think about any kind of utility, I mean, global utility measures, because the ones that we have seen so far and ones that you tried before are mostly, I would say, application specific, right? And then especially the CLVD, the paper, I don't think they did anything about global utility measures. Like they're always looking at particular regression analysis and stuff. But I mean, it makes sense to think about global utility measures. And we're going to talk about the three that the paper talked about, and those questions I think I would just like, I think not about the pros and cons, but I think we have enough examples by now of what we mean by global, at least what we mean by analysis specific, all of the ones that we have seen so far. And I think it's useful and important to think about global because it's also very statistical in the sense that we think about distribution, we think about similarity between distributions, and then different ways to summarize the similarities and differences. So that would be important. And also, I think some of you are just curious or like not sure. Yes, maybe I sort of understand what the method is about, given what the paper is talking about, but then how can I actually compute and then implement? That will be a natural question to ask. And then as you will see that each of the implementations that I provide here will involve certain kind of like, I mean, some other statistical like skills and knowledge, I think will be beneficial overall for your experience in education. All right, so this paper, 2009, the key, I think, the three global utility measures, the propensity score, the cluster analysis, and empirical CDF. The key, I think, what they're trying to say at the beginning of their paper is that they're trying to use methods to differentiate or discriminate between the original and the synthetic. And that, I think, is a natural idea. Like, I now have a synthetic data set. I want to see how good my utility is. In one way to think about it is whether I can discriminate between those two using certain statistical techniques. So the three that they talk about are all available to do that. There are pros and cons of each. I think the paper talks about it as well. You might have your own thoughts or ideas. So let's jump to talk about each of the measures as much as we can today. And then I show you some of the ways that I figure out how you can do it in R, but not complete. And then I personally have other questions as well as I went through the paper, so we can all discuss it. So propensity score, the measure itself is from what people call in the literature propensity score matching. What they usually do is trying to figure out like two groups, pretty much like group A and group B. One of the group has received intervention, and let's say group A, and then B is a group that has no intervention, and then they're trying to estimate the effect of the intervention. And the way that they do it is calculate what they call the propensity score. So if you have two groups, I know one receives intervention, the other one does not, then you can actually use methods to predict based on what you have on the other variables, let's say, to predict, like say, which records you think actually receive the intervention and which records actually have not. And then we can check how good the predictions are. And so the general story, like the methodology here is that you use some methods to predict, as now you probably have noticed, because it's yes or no, because it's intervention or no intervention. Naturally, people are going to use a logistic regression to do the prediction. So we're going to talk about that. So logistic regression, we just talked about it earlier, like an hour ago, is very useful for binary outcome, right? And then here, what they're trying to do is if you have two groups, I can do a logistic regression using the explanatory variables that I have, and then I predict for each record whether they should go to group A or group B, and then I'm going to later check how good those predictions are. Okay, so so this method in particular will have particular steps. So for the if the propensity score is being used as a utility measure, the intervention is synthetic or not. Okay, because you have the original and you have synthetic. So in this context, when we talk about intervention, it's talking about synthetic amount. So I listed, based on what the paper was talking about, I listed like a few steps here, so we can just talk through them and then see what we can do. So we have two groups. In our case, it's the synthetic data and then the original data. Okay. So what people usually do is you merge the two data sets together, and I think they usually do a row bind. So you can have like a double the size, double the rows, but then you still have the same columns. Okay, so that's how they're stacking it. So if the original data set and the synthetic data set, they have the like dimension n by p, and if you stack them together, the merged data set going to have 2n by p. Okay, that just be the dimension, like how you think of it. I raise this up mostly because once you start doing it, you have to think through this, and then those will be useful material. And then what they do is they add an additional variable. You can think of adding another column. So you start with, this is the original, this is the synthetic, so I do O and S, right? And then I have this P. Those are the number of variables that I have in the first place. And then now I created one more column. I call it S, and I code 0 for every observation coming from the original, because it's not synthetic. After S uses synthetic, and then code 1 for every record coming from the synthetic. Okay, so now I have one extra row, one extra column, 0, 1, and then it should be just n copies of 0 and n copies of 1. Okay, so this will be, as you know, the outcome that we're trying to model, because this is the truth in the sense that I know once I stack them together, I have the first half to be original, which is coded as synthetic as Si equals to 0, and then the second half is the Si equals to 1. So they're the synthetic. So now we're going to use a logistic regression model here to pretty much we're trying to model for each observation what's the probability that that record going to go into one of the groups. Okay, and then from there we do a prediction. So what you're going to see later is that you can have, what you're going to have is we have to do a prediction. Let me just use maybe like S hat. Oh, I'm going to use S here. So you will be able to predict for each record in the merged data set the 0 and 1s. Okay, and then we see how good the predictions are using such a measure. Okay, so that's the general idea. Let's see what you can do. So the third step is what we call like for each record. So there are 2 n records. Keep in mind, we're going to compute the probability will be in the synthetic data set. Okay, and then from there we can do predictions, and then from there we can see how good the prediction is. So notation wise, we're using P hat, right, for the estimated propensity score, which is the probability of going to the synthetic, like the probability of being in the intervention group. That's what in the literature is. But then for synthetic data, utility measure, we're using P hat to be the propensity score, estimated propensity score. From there, you can make predictions, and what we're going to do is, oh yeah, never mind. Actually, do we do predictions here? Maybe I'm confusing myself. Yeah, let me take that back. I don't think they do predictions. Mostly they're comparing, sorry about that, they're comparing the distributions of the propensity scores in the original data and then in the synthetic data. Okay, so remember, like, so let me take that back. I hope I can scrap it, like I recorded everything, but let me take that back. What I mean is, what I hope I can, is you're gonna have, okay, so let's see. So this was the original data. Let me redo this. This is the synthetic, they're the same size, so n and n, okay? We create this one extra column, which is S, right? We have 0 for all of the first half and 1 from all of the second half. Okay, so the model, like a lossless regression model, is estimating the p hat 1 through p hat 2n here. So for any p hat I, we're looking at the probability of that record going to become going to be predicted to be in the synthetic group. Okay, so what we mean by that is, so if you imagine like we're going to get a sequence like a vector of this estimations, and look at the measure here. The measure, we use U underscore P, so P stands for propensity score, U stands for utility. What they're trying to compute is thinking about each P, the distance from a constant. We're going to talk about what the constant will be. You will see that in the case that we're like stacking up n and n together, this constant is 1/2. And what we mean, and then you see like take the difference, take the square, and then take the mean. Okay, so what this is really doing, so 2n we know is the number of observations, and then p hat is the estimated. C is the proportion of units within synthetic data in the merged data set. Okay, so imagine if the two data sets are very similar to each other, then the pi hat should be very close to 1/2 for every observation. Okay, if the two, so yeah, so we're using the entire merged data set to do our propensity score estimation. So if the two are like this indistinguishable from each other, then the pi hat estimate will be very close to 1/2, because each observation will have like roughly 50% chance of in the synthetic data set. That means like another 50% chance of going to the original. So it's indistinguishable. Okay, so that's what this measure is trying to do. Okay, so this C is 1/2. We're going to use that for this case. And the lower this UP, the higher the similarity between the two, and then the higher the utility. Okay. On the other extreme, because if the two sets are very different from each other, then pi hat will be either very close to 1 or very close to 0. Right. So if you think of a particular record, I mean, each record will have a high chance, like for a particular record, it's either very likely to be in the synthetic data set or very unlikely to be in the synthetic data set. So that pi hat will be either close to 0 or close to 1. So that will give you a pi hat minus 1/2, close to 1/2. Okay. And you take the square, you take the average. So the UP, the closer the UP estimate is close to 1/4, because it's 1/2 squared, the worse the utility, because the bigger the difference between the two data sets. Okay, so that's the gist of what you do. So this is what I just talked about. We are looking at when you set C equals to 1/2, then a high level of similarity between the two data sets is going to result in UP close to 0, and then low level of similarity are going to result UP to be close to 1/4. Okay, so this will be something we can use. All right, so yeah, so that's the sum. The closer the value to 0, the higher the utility, and the other side. All right, so I'm using an example of the synthetic CE, and I was just doing the simple linear regression case. Okay, so we have the synthesized log income given the unsynthesized log expenditure, and right. So I included the code here. The only other change that I made is I created a new, like I just added one more argument in my synthesize function, so I can set C, because I want to like use the same synthetic data set every time when I'm going through all of the different measures. Okay, so there's a slight change there from what we saw before, but other than that, we have this synthetic one storing one synthetic data set. Okay, and the first column is the log expenditure unsynthesized. The second column is the log income, which is the synthesized one. All right, step 1 is to merge two data sets and add the as variable. I mean, you can have other ways to do this. I would do an R bind, and then I just create a new column with n zeros and then n ones. Okay, and I name it as S. Okay. The second step, we're gonna compute a propensity scores with the logist regression. For me, I was just doing something very simple. So for our merged data set, We have n observations from the original and observations from the synthetic, right? And then we have two variables. One is the log expenditure, yeah, let me do LE, and then log income, LI, and then this S, right? We have the three columns in the merged data set that we have now. So as we talked about, we're trying to predict, or like not predict, we're trying to estimate the PI hat of each observation going into the synthetic data set. So essentially what we're doing is we're trying to model this column of zeros and ones using like other information. Okay. For me, I'm trying to use like both of the predictors, like both variables as predictors or explanatory variables in my model, but you can also add interaction terms. Okay. So you can build the logistic regression as complicated as you want. And so that will be, but this is an example. And if you want to try, you can do the interaction term as well. And so this is the model itself. And one thing I want to mention is that for the estimation process, actually, I didn't use the Bayesian model. I guess we could, I mean, because you can always also get the predicted PI hat from the Bayesian model. I don't know which one is preferred. I mean, I think like the GLM, which is the frequentist logistic regression, is like simple to do and it's a one line. But that might be something maybe one of you want to dig into for a project if you ever want to like explore this. I mean, for me, when I was reading the paper, I thought let's just do it. GLM. I think it's easy enough. But I don't know if there's a big advantage or disadvantage of using the Bayesian method here. Okay. But we already saw how you can do the Bayesian method earlier. So you can easily do another one from the Bayesian point of view. But if you want to do a frequentist classical logistic regression, you can use the GLM function. And in it, you supply your response variable, which is my S, right? That's the binary outcome that I'm trying to predict or like model. And then I'm having the two predictors, both of the variables that I have. So when you're doing a logistic regression, make sure that, so GLM stands for generalized linear models, okay? And they have all of the different families in terms of your modeling. So this binomial, you probably remember earlier we talked about, well, when you have binary outcome, you can consider them as one and then PI, right? So this family refers to that model. Okay, so because we're doing binary, which is the logistic regression binary outcome, you do a binomial family, and then the data is what I called it earlier, merged data. Okay, so you get the logistic regression, I name it here as the output, but you also need to, we also need to make sure that we're able to get the p hat. So this is where we come back to this equation again, because in fact, when you do so, in fact, I should say, in R, there exists this function called predict, that if I have, so remember this is the regression output, the logistic regression output that I saved in it. And if I also just supply the data, this function gonna give me what I call like later saved in predict, and that predict gonna return us the B0 plus B1 times X1 plus B2 X2. Okay, so it is returning us this, not PI directly. So that's why we again have to look at this algebra manipulation, because we want to get PI themselves or PI hat. So you have to do one more line over here to get the PI. Okay, so from there, the PIs will be, so the props will be the one that we're able to compute that UP measure, right? So I'm just following that formula. I didn't include it here, but you can then compute it to be, in this case, pretty small, close to 0. So we know that the closer the UP is to 0, the higher the utility, right? And then the closer it is to 1/4, which is 0.02, 0.25 in this case, but it's definitely like very close to 0. So that means the logistic regression model cannot really distinguish these two data sets when you stack them up together. Okay, and then that indicates a high level of utility of the simulated synthetic data. Okay, all right. Yeah, sorry that I'm rushing a lot. I think it's 5:10 now, so I'm going to stop. But the slides is ready on Moodle, on GitHub. So if you want to take a look at them to implement the rest, feel free. I mean, because part of the required exercise for today's lecture is implementing as much as you can. But now we know how to do the propensity score. The other ones I posted there, so you can try that. I think on the CE synthesis that you did, because you haven't done much about the for the data set that you chose for your project yet, so you can play with those. And so for next time, we're going to talk about the other two measures, and then I will also introduce some stuff about when you have multiple synthetic data sets, like we're talking about like M equals 20 or 5. Why do we want to do that? And then once you get multiple synthetic data sets, how can I say, natural question is if I have 20, I'm gonna have like utility measures for all of the 20. How can I get a valid combined outcome? Okay, so that will be, so I have a couple of pages things for you to read, but that was just for next time. So everything else that you haven't got to do, like by far, like you can catch up and then get this stuff ready on GitHub. Okay. All right. And here, and yeah, see you guys next time. Take care, bye. I realize I'm waiting, but you will never see me waiting. Never mind. See you later.